Hey everybody, this is Larry, this is me going with a very tough Q4 on the weekly contest 339, minimum reverse operations. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about this problem. So this one, to be honest, at its core, I didn't think was too difficult. No, I'm lying. I thought it was April Fool's, right? No, I mean, this was very difficult, but I think algorithmically, it's not super difficult. It's just about a lot of implementation and getting indexes right. I'm not going to go over all the details of certain formulas, but I will try the best I can because there's some stuff that I think you can see in a little bit. So I'm just going to go over the explanation in terms of the code because I think algorithmically it's pretty straightforward. I mean, it's not really, but in theory, the theory could be straightforward. The biggest part is that for me, it's actually just a breadth first search, right? So that's why this is really simple, quote unquote. I mean, it's very hard. You look at the stats here up here, and you can see. I mean, this is 2,000 submissions and 53 is right? But it's a breadth first search problem. It's a very hard one because a naive breadth first search, given that this is n, it's going to be n squared, right? So the thing that we're trying to optimize, the way that I try to optimize it, is by doing it in a way such that we don't need to check every node, right? Or every edge. So a way to kind of remove all the edge implicitly at once, right? So that's basically the idea. And there are a couple of ways you can do this, and there are a couple of observations to kind of speed this up. For me, for example, is that the parity, right? If k is equal to even, actually I have some notes here, let me double check just so I don't say something wrong. If k is even, the parity always changes, right? Meaning that if you're in an odd space, you always go to even space. If you're in even space, you always go to odd space. If the parity is odd, you always keep the same parity, right? Meaning that, if you're in an odd space, like if you're at 1, you can only go to 3, 5, 7, ... for k is equal to odd, right? So one optimization, the first optimization that I did is breaking it down to 2. I'll go over the rest of this in a second, but yeah. And the other thing that I do is that I'm trying to, like I said, optimize for not checking whether the same node exists twice, so that it'll be n squared. So the way that I did it is with by having a sorted list. The reason why I have a sorted list, and in other languages it may be a little bit different, you have to be a little bit careful, is that basically the core part of this is the visualization of this is pretty straightforward, right? Maybe not, but I'm telling you in a way that's straightforward. But basically, for example, you have like this, for some k, for k is equal to 4, say, you only really have to look at, k space to the left and k space to the right. So the reason why I have a sorted list is that so that I could binary search whether for all the cells that we haven't been to before, to the left and to the right, and then do a regular breadth first search with them. And that's why I have a sorted list, and I kind of and that's basically what I did. And the reason why I have this xmod 2 thing is, as I said, because depending on k, you can only go to other odd spaces or other even spaces. So why not just put them all in, or I separate them out so that you only need to check each cell exactly once. Because as soon as you check whether it exists, that means that you're visiting it, and then you can remove it so that it doesn't get checked in the future. Hopefully that makes sense, but basically I'll give you a really short example. It's that, let's say, you have a 0, and in theory, let's say k is equal to 11, so that means that you can go to the right 1, 3, 5, 7, 9, and 11, right? It's not actually, because you can, there's some stuff about pivoting, but let's pretend that's the case, right? So that means that if we do a binary search, this will all come up, and then we put 1 on the queue or something, right? Or maybe another way is 2, 4, 6, 8, 10, right? So next time we put on the queue, we put all these things. Oh, that's a 10. Next, we put all the things on the queue, but then now we're going to search. It's going to go from 4, 6, 8, 10, 12 or something like this, right? But of course, we do a binary search because we already removed it previously. when we do a binary search, none of this will exist. And then so when we do a binary, or when we process the 2 node, it's only going to see 12 and not 4, 6, 8, 10 and all this stuff. So therefore, this is the way I optimized, so that you don't, if it doesn't become v plus e, it becomes O of v, log v, because you have to do a binary search. But that's basically the idea. 2 binary searches, I guess. Yeah. So that's the part about this part. I removed the initial node because we set it to 0. And then I also remove all the banned ones. So that's also how I handle this a little bit easy, right? Is that because we already remove all the banned nodes, then when you do a binary search, the nodes would just already be missing. I'm not going to go over this quite yet, but yeah, give me a second. So, so now the rest is just going to be breadth first search, right? And this is a little bit hard to kind of figure out for me. But basically, this part is just try to calculate the spaces we can go to the right. So let's say again we have someone like this. Well, the spaces that we can go to the right depends on how many spaces we have to the left, right? Let's say k is equal to 5, or let's just say 8, right? Something bigger. Well, that means that here you cannot, even though okay, that's actually k is equal to 9, so that means that we can move 2, 4, 6, and 8 spaces to the right and left, of course. But in this case, you can't actually get here to this spot, because if you just count the number of 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, actually, wow, that's all of them, so let's just add more. But if you kind of take the leftmost 9 and then you flip them, well, the best you can do is get here, right? So that's basically what I did. Is that I basically did some maths. You could kind of prove these maths. I'm just saying, but what this is saying is that this is the number of space I have to the left. Well, the number of space I have to the left is the number of spaces I can move to the left of the right side. You can kind of prove this form, or just like derive it. But basically, yeah, if you have more space, for example, if this is here, then you're able to kind of get closer, right? So that's basically what this function is doing. And then here is just going to the space to the so if you have enough space, then we just make sure that this space is just to the right of the current space. That's all, right? We have +1, and then we just keep making sure the parity and stuff like that. And yeah, and basically yeah, we'll go over the override again in a second. But now we have 2 numbers that we go to. So basically, write 1, write 2 is just basically me trying to say, okay, now this 1 can go from some range to the right that looks like this, right? Like, let's say this range. And then now we binary search on the list that we have on those 2 numbers, right? So, we do a binary search here, we do a binary search here, and then that's it. And then we go through the sorted list. For each number in that sorted list, we do regular breadth first search stuff. We update the distance, we update the queue, and then we set it up to be removed. I did it this way because I believe you cannot, because this would be really funky if I removed it in the middle, because then it like throws off the indexes, right? So that's basically why I put it in an array, and then I kind of remove it later. I do the same for the left side. This is just going to the left side. It's the same thing, so I'm not going to go over in detail, but see if you can derive the formula at home. Everything else looks exactly the same. So what is this override for, right? That's the only thing that I've left. To be honest, I did this override because I couldn't figure out the formula. So I basically, for me, it's the other. So this one is you cannot go too close to the 1 because you don't have space to the left. But let's say your space is like something like this, and your k is say 5, right? Well, if k is equal to 5, you also cannot, even though let's say k is equal to 6, so you can move 1, 3, and 5 moves, but you cannot move 1 to the right because you just don't have enough space, right? You need at least like this. One more. Yeah, you need this. Oh, no, you need. I don't know, something like this, right? So you need this to move the one to the one space to the right? But because we don't have this, what I did, and I spent like 10 minutes trying to figure out this formula, and I wasn't able to successfully find it. So actually, I just calculated manually by looking at the last k cells. I reversed it and then calculate the most we can go to the right. The most we can go to the right, and then I checked it and then make sure that we overwin it if this is too close to the border, and then that's it. So instead of using a formula, I kind of just wrote the code for it and let the computer figure it out for me is the answer. So what's the complexity here, right? So each number can only be so as soon as we do this binary search, or as soon as we process each number, it's going to get removed, right? And each number can only be looked at once to get removed and once to get added. So that means that this is going to be n log n time in total. And that's pretty much it, really. Even though there's this loop and this pop, everything is n log n in total, and that's it. Like I said, the idea is not that hard, but a lot of it is implementation. I did a lot of implementation-y things. So yeah, I'm gonna make this a little bit smaller so you could see at least the top half. This is the setup, and then if you want to pause and this is the breadth search. Looks okay. You only look at this half for the right side, and then this is the right side. This is the left side, and that's pretty much it. That's all I have for this one. Let me know what you think, and you could watch me solve it live during the contest. Now, I struggled a lot, so you could maybe see how I figure out each piece together. But let me know your comments. Boop. Minimum reverse operations, okay. NP. Okay, so there are a bunch of zeros and one. You're given a band array. The I position in band. Fine. In one operation, you can choose a subarray of size k and reverse it. Okay. People haven't gotten this yet. It's actually surprising. The one in position I. Oh, to each I. Seems like it's just by first search. Well, it is by first search, but there can be n square things. So you have to be a little bit smarter. Or like there could be a buffer search, but how do I think about this? And you just have even without banned things, I guess what would it look like, right? I don't think this should be just like DP, but with more math, right? Maybe not. Well, if K is, let's see it. If it's 2, then you could just do all those, right? If it's 3, then do you ever want to go back? I guess you kind of want to, right? So you have 4 then, and you want to rewrite 3, then it's 1 0. 1 0, maybe you have a 0. If K is odd, there are some like a lot of special cases for sure. If K is even, then the parity is just that. K is even. What does that mean? No, it's not an odd even thing. Maybe. I think still haven't gotten it yet though. How am I doing anyway? A rice on the top, not surprising. I was doing better though, but I guess I was a bit slow in Q3. Alex haven't gotten it, I don't know. Do you ever want to be able to go back? I think the answer is yes, but it's such a weird case, isn't it? What about 4, right? Let's have 4. And now I can just go here, okay? And now I can also go here, but then now I can go back, so it's not just strictly forward. This is a case analysis. So we can't, it's not just one direction. You have to be a little bit smarter than that. I still think it's ad hoc E, but is there a way I can be smart about do a binary search maybe? It's part of the buffer search. That would be a cute idea. If we have a sorted list and then we just remove everything that we can go. Right? then if k is really, you just have to check for some of these, which is the tricky part, right? I think it's just for search of a small binary. Like if you do a sorted list, yeah, maybe. Okay, let's see. It does something, maybe not enough, but okay. And I think one case I wanted to put was maybe 10, 4, and then just empty. Okay. 10, 4, I don't know, 0 and then 4, oops. Okay, and then basically where can I go, right? So given k, say k is 2, right? So naively, it is, you can go to k minus whatever. But what if you had a wall? Okay, so this is tricky. Has anyone gotten it yet? So the left you can go is you go to the max of 0, and then now minus k plus 1, or yeah, but if we're too close to the right, then we have to this and close. So that means that if we're n minus now, okay, so if k is 4 and we're at 0, then you can only go to plus 3. If p is 1, then you can go to plus 1. That's the part that I don't know how to do the math on, maybe. So for k is equal to 4, a thing can go move 1 and then 3. Okay, so k is equal to 4, you can move 1, 3. If k is equal to 2, you can move 1. If k is equal to 3, you can move only 2 spaces. So there is some like odd even thing here as well. Is that true? No, because now you could do 3, 1, 3, 1, so you can still get to the 2s, but just very awkwardly. And we want to kind of divide out the odd evens as well. Still no one got it yet, but also people have been submitting for some reason. A lot of people are trying. Okay, what about k is equal to 5 then, just to make sure. K is equal to 5, then let's see. Can move 4 for sure. 4, and then can you get to 3? Oh, you can move 2 for sure. Okay, so 2 and 4. But there is an even odd parity here. This is kind of a hard one. Okay, fine. Okay, so basically you either don't move or you always if it's even you always change parity, and if it's odd you always keep the parity. Okay. Okay, fine. Actually, I guess I could just do something like, what was it? Right, and then now we can just do quick, guided ones. Okay. The left bound thing still checks. Okay. So it depends on how close we are to the border. On the left side, it's actually not n minus now. It is now. If just now, right? So basically, if we are 0 distance away, we can only go +3. If we have 1 space, then we can go +2. 2 space, we can, well, just stay the same with a 0, which I guess doesn't do anything. How do you do the math on this? Especially when you have more things. So basically, now going to the no, I did it the wrong way. Maybe like a different way first. Alright, let's do the right first. So it has to be min of n minus 1 now plus k minus 1, right? And but if we are so max up this, now we can always go go here. I think that's why I'm confused. Oh wait, is that true? I think my things are wrong. So we go to the right. Yeah, we can always go plus that. But basically, for every space to the left, we can go subtract 2, right? Okay. Oops. Move k minus 1 to the right. For every space now left, we can check minus 2. Okay, so right. Has anyone gotten yet? Oh, 10 people gotten it, so okay. So now I have, I don't know. Is equal to, so this thing minus, so for every space now times 2, and then we want this to max of now, right? Now plus 2. Is it plus 2? Well, it's plus 2 because it's plus 2 if now plus 1 plus k mod 2. This is a ridiculous thing. Okay. Okay, so let's just print now right 1, right 2 on the things that we can do. Oh, of course. Okay, so from 0 we can go to 3 and 3. Okay. Let's try again with 1. I should go to 1, 3. Oh yeah, I mean you should go 2, 4. So that's correct, I think. Okay, and then now wait for okay, so now we want to SL of right 1, right 2, dot bisect left, right 1, right. I mean, they should be the same anyway, so. Index, but then also yeah, pen SL index and answer of okay, fine. Oh man, guys, name stuff better. for x in nxt, and now we move x. Okay, this isn't quite completed yet, but it should at least set some stuff, so we'll see how that goes. What does that mean? Tell me what? Oh. Okay. Don't know if this is so for 4. I think this is actually roughly right, maybe. Don't know if that's true. Actually got this one right, so. Okay, and then now we have to do the same, but for the left. Okay. Okay, left 2 is equal to max of 0 or now minus k plus 1, and then now we want plus n minus now times 2. Minus 1 times 2. And or just now minus 1 minus k mod 2 again. Okay. Let's do now left 1 left 2. That's no bueno. Is this right? So right 1, if now it's all the way to the end, this is obviously not going to be right. But I guess it doesn't find anything here in that case. But still, very awkward. What am I trying to say here? This is this amount. This n minus 1 might not be right. Oh, but I guess we bound it anyway, maybe. I don't know if I like this one. Let's remove this, and then I think I don't need the thing, it's fine. I don't need to bound it because the search won't find it if that's the case. The binary search. Keep it simpler. Okay, so it goes to, on the left side, it goes to, yeah, mix this up. So, okay. I tried to do it from symmetry, but actually, is this case, yeah, yeah, and it could be 0, but or negative, but that's fine. And then here we actually want this plus this but we want the min of this, and now minus k, or now minus 1 minus k mod 2, maybe. I guess that's probably technically right, if we don't count the bounds. Alright, let's try this not one, right? But instead we want 10, right? Oh, whoops, I meant 9. Almost hit submit by accident. That would be very sad. So 9 can go to 6. From 6 to 6. Okay, that actually checks. If we go 8. Then 9. We start at 8. Wait, what? Oh, yeah, it started 8. We can go to 5 and 7. Is that true? 8, 9, 7, 6, 5. So then this for k is equal to 4. So you can go to 7 and 5. Okay. I mean, maybe I believe it. Okay. Yeah, there's probably some code reuse things here, but okay, is this the right answer? At least for the it's right answer for the thing. 4 is to the 1. Okay. Oh, I did. No, I checked ban by not making it possible. I'm going to YOLO submit. Not 100% confident. Shouldn't time out, but that's actually sadder than timing out. But that actually maybe is fixable. I think maybe I just have something weird. Maybe I misunderstood this one. So 4 and 2. So 4, 2, and 2. Why is that? Well, why am I getting it wrong, I guess? Oh no. Why am I getting it wrong? So 0, 2, and it is 1, 0, 0, 0. Am I misunderstanding this problem? Oh no, it gets to 1, 1, 0, 0. Okay, I see. I'm getting weird things on the edge. So maybe I'm off by 1 on somewhere. Okay, I mean that's, I wouldn't say it's fine, but it's fixable. Sad, but fixable. Okay. So 2 can go from 3 and to 5. Okay, that's fine. 3 can go to 4 to 6. 3 cannot. Oh, I didn't check. No, this is wrong. This is wrong. I mean, it's the right idea, but I have to do a few more checks here. Okay, so it goes to the right. It can only go. Okay. How are people doing anyway? Okay, I have to do more checks, but I think the idea is fast enough. I don't know how long. How many? They don't tell you, do they? Okay. Okay, I see. So basically, it's saying that 4 to 6. That's not quite right. Basically, you can only go. This is so annoying. How much time do I have? I have 50 minutes. I should be able to fix this, but I am. This is like this maybe like a 10 wrong answer kind of day. But okay, I know what's wrong. Okay, so we are at. Actually, this doesn't even go to for k is equal to 4, it doesn't even go to 5. It doesn't even go to 3. So this is wrong actually, and that is going to the right. And basically, it's saying that so it should be. I thought that going out of bounds is fine, but actually it's not. How far can we go? This is so hard to get right. What is the math that I'm thinking of? Okay, so at 2, we can go to 1, that's fine. We cannot go to 3, because it is, I can go 1 and 3, but 1 is only available if we can go just 1 more to the right. So that means that I thought that going out of bounds would be okay, but you can't go up. So we need at least 1 space to the left. Okay, so this part, I think, that is the space. Basically, this. Oh. But then we also want. Okay, so there's that. Okay, so if we want to go 1 space to the right, we need 1 space to. We need 2 space to the right. We want to go for n is equal to 4. Okay, let's see, right? So k is equal to 4. If we want to go k, if we want to move 1 to the right, then 3 more space. Does 3 more space? No, then at least 1 more space needs to exist. So that means that for me to do that, I need, for me to move 1 space, I need 1 to the left and 1 to the right. Of the querying space. For me to go right, do I have a formula? How to express this formatically? Okay, that means that the thing is that if we don't always remove, then it's the complexity may become time limited. That's why I'm worried. Otherwise, we could just do an if statement check and. But no, that becomes n squared if we don't remove. Okay, yeah. Basically, we want to set up right to. So this is the max, but then we want this to be min of this, and so k is equal to 4. For every space that we get, to, so of course we want to move 2, well we can't, but we want to move 3, we need 0 space. So basically it's going to be K, so we okay, so we want to move 1, we need 1 extra space, but if we want to move 3, we need no extra space. Okay, that's okay. What if we have K is equal to 6? Then for 3 we need 2 extra space, right? Because okay, I see. So then this is going to be something like I'm supposed to move this one. I think, well, I mean, I think it makes sense to, no, not really. I don't know. People are getting a bit, I don't know. Okay, so maybe I'm max of this, and so we have the now space plus K minus 1. No, it should be something like n minus now is the number of free space we have. No, n minus now is the number of space that we have. Let's see. K04. I think I'm just trying too hard to come up with a formula, but maybe I can just simulate it. Right. Okay, let's see. Right. Okay. Okay. Wow, I spent like a long time on this particular one. Okay. What I want to do? Come on, Davey. What I want to do is let's see. These are terrible names. Thank you. Okay. Three can go to 0, 2 can go to 1, 1 can go to 2, okay. 0 can at most go to 3. Right. Yep, okay. Maybe I just need to do, was it? I think that one's wrong actually. Alright, last 4 numbers. Yeah. Okay, I didn't need to reverse. Okay. What do I do? 6, 7. Wait, what? Oh. Okay, maybe I did need to reverse to find out. Or maybe the other way around, I forget. Trying so hard for this formula, so that's why. Okay, that's quite wrong, but okay, fine. Okay, fine. Can't figure out the formula, so why not just simulate it, right? Okay, so then now on the right side, if do we want min? No, we want max on the left side, and so we want min on the right side. No, do we? Yeah. Oh no, we want max. Yeah, and then this one, I guess we want min. Yeah, okay, no, that makes sense. Still wrong answer for this one though, so no Gucci. It's going to the right, so let's see. Okay, so 2 can only go to 1 on the right side. So that means, oh, so that means I want to make right 2, not right 1. And then I want min. That's why, okay. Yeah, okay, fix that. Is everything else right-ish? This one's right, this one's right. I don't know if these are right, to be honest. Which one is this? Is n is equal to 4? I feel like that's wrong. Because we could go 3, 3, and then 3, right? So just swap this and this should go to... So something else is wrong, but I think we're at least solved this particular case, which is good. Okay. Making progress very slowly, but technical difficulties. Yeah, this should be do, and then do. So maybe I'm off by 1 somewhere. Alright, let's do 10, 0, 4, right? Is that it? And then basically now, so this should be going from 6 to 9. So 6 and 9 on the right side. That's 7, 7, huh? Oh, whoops. Okay, fix that and that and that. Okay. Let's get rid of some print statements. And then it's time to YOLO again. If it times out now, I'll be very sad. Okay, cool. Whew, that was a hard one. Yeah, everybody, thanks for watching. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem set, this problem, the explanation, and everything in between in the comments, or Discord. Prefer Discord just so that, you know, it's more interactive. But yeah, otherwise, stay good, stay healthy to good mental health. Hope you have a good or great rest of the week and the weekend. I'll see you soon and take care. Bye bye.